So in this part of the lecture, we will talk about distillation columns and their sequences. So you will need to recall the material that you have learned in distillation and absorption, or will learn in multi-component engineering separation units. So just to remind you that you have learned in binary distillation that normally you have two components and then you have one column, and then you have to define the distillate product specifications and the specifications of the bottom product of the reboiler. And normally we use McCabe-Thiele method to design these distillation columns. We can also have situations where you have more than two components, and that's what we call multi-component separations. And you are already learning that in multi-component engineering separations unit. So let's take an example of a three-component mixture for a multi-component distillation. So normally in multi-component distillation, we will require more than one column to separate these components. And normally the rule is that if you have n components, you will require n minus one columns in the component. So for a three component mixture, you will require at least two columns. If you have a four component mixture, you will require n minus one would be three. So you will need at least three columns in a sequence. Okay. Another important thing to remind you is that when we are talking about multi-component distillation, we always have to identify two key components of that mixture. So we have the light key component and the heavy key component. So light key component is the one that we want to keep out of the bottom products, and the heavy key component is the one that we want to keep out of the distillate product. So as a 2 degree of freedom, we can specify the, the the composition of these light key component and the heavy key component in the distillate and in the bottom product. We don't know exactly the compositions of the non-key components. We can only define the compositions of the heavy and the light key components. So here, for example, we have a mixture with three components A, B, C, and we want to separate A from C. So that will be our main separation. It means that A will be our light key component and C will be our heavy key component, while B will what we call is as a non-key component. It means that we will focus on the separation of A to C, A from C, and B will be distributed between product and bottom product and distillate depending on its relative volatility with respect to A and B. Okay. So if we look at this separation sequence now, so for three component, we will require at least two columns. So in first column, let's say we decide to take out the light key component, that is A, and the remaining two components B and C, we will feed them to the second column where we will have BC as feed, and then B can be taken out as a top product, and C, because it's a heavy key component, so it will be in the bottom product. Then as a second sequence, we can have, instead of taking out A from the distillate, we actually decide to take out C first in the bottom product, and the top product of the first column will be the feed to the second column, and then we can separate A as the top product and B as the bottom product. So depending on if we decide to take out light key components first or heavy key components first, we can also define direct sequence or indirect sequence. So sequence one is a direct sequence, and what are these direct sequences? Direct sequences are the sequences where we decide to take out the light key component as the distillate of that column. Okay, so here we have A as the light key component, so A is in the distillate. In the second column we have B and C, and B is relatively lighter than C, so B will be taken out as a distillate product and C will be in the reboiler product. So these columns where we actually, these sequences where we decide to take out the light key component as distillate are called direct sequences. Then we have the other case where we call indirect sequence, and indirect sequences are where actually we decide to take out the heavy key component as the bottom product first, and then we look at the light key components. Okay, so here, for example, we have taken out the component C in the first column, and then we have obviously two feeds. So A will go to the distillate, while B will go to the bottom product. So where we focus on the heavy component first, they are known as indirect sequences. Okay, and now let's have a look at a bit more complicated system. So here we have four components, and as I said that normally the number of component dictates the column in the sequence. So if you have four components, then you will need at least three columns. Okay, and in these three columns can be arranged in five different sequences. Okay, so here you have A, B, C, D. So in the first direct sequence, first you decide to take out component A, that is the light key component. Then you have the remaining other components, and then in the second column you decide to take out B as the top distillate product, and then the remaining C and D will be the feed to the last column, that is the third column, and then you decide to separate C into the distillate and D into the bottom product. Similarly, you can have other arrangements where you like, for example, let's talk about the indirect sequence. So here you decide to take out the heavy key component first, that is D, instead of the light key component. That's why we're calling it indirect sequence. Again, in the second column, you are again taking the heavy key component first, and in the last column you are separating the remaining two components. So obviously when the number of components are small, then we can easily calculate how many number of columns or number of sequences we need. But if we have, let's say, 10 components or 6 components, then obviously it becomes more difficult to calculate different number of columns and sequences. So in that case, we use a formulation that you will discuss in much more detail in multi-component engineering separation, but here I'm just introducing it. It's called a King's formula, and King's formula is where, if let's say you have C components, based on the number of components, you can calculate how many sequences are possible. Okay, so if you put, for example, 4 here, and your C will be 4, so if you calculate the n number of sequences, so if you calculate the number of sequences you will have for 4 components, you will have 5 sequences. So this formula is very helpful in calculating how many sequences are possible for based on the number of components. You will study or will have studied sequence selection in multi-component engineering separation unit. So this is just a short recap. So the reason we are looking at distillation sequences is that, as we discussed in the last slide, that depending on the number of components you have, there are many alternative sequences, and they don't all perform equally well. Okay, and it could be a huge amount of work to evaluate all those different options. So we are looking at how we can find the best sequence without too much engineering effort, but without losing the good solutions as well. So first of all, before we actually start choosing the sequence, we need to exclude certain options by thinking about practical constraints. And these practical constraints come from the book of Robin Smith. Okay. That is also our textbook. First of all, if we have a hazardous component present, every column that contains that hazardous component is itself adding to the hazard. Okay, so we would like to take out that hazardous component as early as possible from the sequence. Secondly, we consider components which react, polymerize, or are heat sensitive. Okay, so the more we have them in the sequence, the more damage we are going to do. Okay, therefore again we would like to remove these components early in the sequence if obviously it makes sense to do so. Thirdly, if we have components in columns that are corrosive in nature, so every column they are in need to have special material of construction. Okay, or we will introduce other risks. Again, we try to minimize the number of columns in which the corrosive compounds are present and remove them early from the sequence so that we can actually contain the problem. Fourthly, if we have compounds which are heat sensitive and decompose, their decomposition products become an impurity. Generally, those impurities tend to heat towards the bottom of the column. Therefore, we would prefer to take our desired product from the top of the column, not the bottom of the column. And this is just to avoid contamination. The fifth point to consider is that if we have compounds which polymerize, it is common to add a polymerization inhibitor to the column. Again, we don't want that the inhibitor contaminate our column, and that is why we removed our desired product from the top of the column, not the bottom of the column. And the final point brings our attention to the point that low boiling components are difficult to remove in the system, because most of the time these low boiling components require refrigeration to condense, and it means that all the columns that contain these low boiling temperature components, they require refrigeration. And refrigeration is far more expensive compared to cooling water or other high temperature utilities. So we prefer to remove these low boiling materials early on in the sequence, so that the downstream columns don't have to handle these light components again. Okay, so by removing them early on, we can operate the rest of the columns with a relatively low grade cooling utilities like cooling water and air or something like that. So the take-home message from this part is that for multi-component separation, there are many alternative sequences, okay? And obviously, we don't want to spend a lot of time evaluating all those sequences. So these practical constraints can help us reduce the number of options, or can help us find the viable options only by considering these factors that I listed on this slide.